So next talk is by Federica Sassano on the nature of the first supermassive black hole seeds.
Yes. Hi to everybody. Thank you for this opportunity. Can you hear me? Can you see my slide?
Perfect, thanks.
Thank you. So I'm Federica Sassano. I'm a PhD student at Sapienza University of Rome. I will talk about the nature of first supermassive black hole seeds. Recently, one of the most distant quasar has been detected at high redshift, at redshift 7.5. And it means that these supermassive black holes with typical masses of 10 to the 9 solar masses must have formed in less than 700 million years after the Big Bang. Currently, the existence of such massive black holes represent one of the most hot topics in astrophysics. If we take 5 of the most distant and massive supermassive black hole at high redshift, we can ask which is the typical mass expected for a single progenitor or a single black hole seed around the epoch of formation of first stars and black holes. It means around redshift 2030. If we assume an unimpeded Eddington accretion rate onto this seed, we can go backward in time and see that typically the mass expected for this black hole seed is expected to be 10 to the 4 or more. But this is a very optimistic assumption, both because actually we don't know the nature of these black hole seed progenitors, but we expect that a multiplicity of black hole seeds could have originated a supermassive black hole at high redshift, and both because we expect that these seeds in very gas-rich galaxies, which are at high redshift, could have accreted at super-Eddington flows. In my talk, I will focus only on the nature of these black hole seeds progenitors. Theoretical work mainly suggests that 3 kinds of black hole seeds can exist in nature, among which light seeds, which have typical masses of around 100 solar masses, which can form from the collapse of pop-tree stars, which can form in those environments where H2 cooling is available. The main qualities that this environment must have, we need as first that Lyman-Werner radiation from the background must be under a certain critical threshold, and in order of not ferment the H2. And we need that the lack of metals and lack of dust to gas mass ratio. If one of these properties is present, we need that this must be under a certain critical threshold. In more massive halos, if we have a certain amount of Lyman-Werner radiation, and if this is over a certain critical threshold, we can have the direct collapse of a cloud, which leads to the formation of a supermassive star, which can continue to gain mass from the hot envelope, leading to the formation of a heavy seed with typical masses of around 10 to the 5 solar masses. In the same kind of environment, if we have a certain amount of dust-to-gas mass ratio, we can have the formation of a dense stellar cluster, because dust is able to ferment gas to high densities. Hence, we can have some stellar runaway collisions, which lead to the formation of a medium-weight seed with typically 10 to the 3 solar masses. Once we know the condition that lead to the formation of each channel, we can follow their formation in high redshift galaxies and their connection and their involvement in the formation of a supermassive black hole at redshift 6. To this aim, I've adopted a semi-analytic model, gamete cohesive of dust, which is able to reconstruct the dark matter halo major tree of a quasar host. And in particular, we are talking about a dark matter halo of mass typically of 10 to the 13 solar masses, an extremely biased region of the universe. Once we are able to reconstruct the major tree, this code is able to follow star formation, chemical evolution, black hole seeding, feedback, and so on. In this model, we have implemented an homogeneous treatment for metal diffusion, which is a highly homogeneous process, in particular at high redshift, and Lyman-Werner background fluctuation. This because it is well known that these fluctuations are tightly connected to potential hosts of medium weight and heavy seeds. These are the critical thresholds we have adopted in order to see where the critical threshold adopted inside our model. And we have run 2 different simulations adopting two different models, two different critical thresholds for the Lyman-Werner background of 300 and 1000. Now I want to show you our results, the redshift distribution for light, medium weight, and heavy seeds, adopting a critical threshold of 300. And each panel shows two different histograms. The lighter ones are the all black hole seeds that we can form in our simulation, and the darker ones represent only those black holes that merge to form the supermassive black hole. It means only black hole progenitors. We can see that light seeds start to form early down to redshift 19, when the increase of the Lyman-Werner background radiation suppress POP3 star formation, while heavy seeds and medium weight seeds continues to form down to redshift 15, where all seeds stop to form due to the metal enrichment. It means that all the volume of the simulation is filled by metals. In particular, if we focus only on the darker one, we can follow it means the progenitors, we can follow evolution of the total nuclear black hole mass as function of redshift, which is the black solid line. The gray area represents the minimum and the maximum of the mass available at each redshift. And the colored lines represent different contributions coming from heavy, medium weight, and light seeds. We can see that at very high redshift, above redshift 20, light seeds dominates on the total mass. Once heavy seeds start to form at redshift 20 down to 16, we observe that heavy seeds dominates on the total mass, while below redshift 16, only when all seeds stop to form, only thanks to accretion we can reach the final mass of the supermassive black holes. Medium weight seeds is important to stress that are always subdominant. By increasing the critical threshold of the Lyman-Werner radiation to 1000, we observe an increase in the total number of light seeds that we can form in our simulation. And this is due to the fact that we are increasing the star formation efficiency, and we observed a decrease in the total number of medium weight and heavy seeds which can form. This is due to both to the higher critical threshold for the Lyman-Werner radiation, but also to a more efficient metal enrichment. Now, recently a new work was released by Chon and Onomukai, where they have studied the impact of metallicity on accretion onto supermassive star. And they have observed that for very low metallicity and high metallicity down to 10 to the minus 4, thanks to the higher accretion rates, supermassive star can still gain enough mass in order to reproduce a heavy seed. And the same can be inferred for a medium weight seed, which can still form for metallicity of 10 to the minus 3. So I've taken the results, which implies a wider range in metallicity where they can form heavier seeds. And I ran two different models, adopting these two quantities of the critical Lyman-Werner radiation. I labeled this SKA as super competitive accretion. And I want you to show the comparison with our model. We observe an increase in the total number of seeds which now can form. This is due to the more favorable black hole seeding conditions, but we observe a decrease in the total number of heavy seeds which can form in the model SKA 1000. To understand why, now let's see the implication on the total evolution of the nuclear black hole mass. Despite the larger number of seeds which can form, in SKA 300 model, we can still reproduce, and the evolution is similar to the previous case, and we reproduce the final mass of the supermassive black hole. But in SKA 1000, we observe that the final mass of the supermassive black hole is not reproduced. In this model, we observe that medium weight seeds are comparable in mass to the heavy seed one. And to understand which is the implication, I need you to show the black hole mass function at redshift 15. It means when all seeds stop to form. The average black hole seed mass is the vertical line. In this plot, I show the different models I showed you before. And vertical lines show the average black hole seed masses. It means the average black hole that we have at the last epoch of seeding formation. we observe that in SKA 1000, this is the lowest value, and this means that quality but not quantity is an important parameter in order to establish if the final mass of the supermassive black hole is reproduced. Finally, in this work, we have addressed the formation and evolution of 3 different black hole seed populations within a self-consistent cosmological model. And these black hole seed populations are strongly connected to each other. We observe that heavy seeds provide the dominant mass and contribution, and that quality but not quantity is a key parameter to establish if the final mass of the supermassive black hole is reproduced. Also, if black hole progenitor represent only the 10 or 20% of all black hole seed population, also the satellites can provide a catalog of black binary systems detectable with the 3rd generation GW telescopes. Thank you.
Thank you for a nice talk. We have a couple of questions on the Slack. So first question is about mergers. Could you clarify what role did the massive black hole mergers play in the model?
Okay, so you mean, as you can see, merger can play an important but not dominant role, because the dominant role is accretion. But merger can be important at very high redshift, because if we reproduce a massive black hole above redshift 15, this can be very important to define the the following evolution of the nuclear black hole. So we observe that accretion is the most important parameter despite merger.
A second question is the number of black hole seeds in your model consistent with the number of observed quasars?
So quasars are is the final mass that you want to reproduce. Actually, we are defining seed at very high redshift, and you cannot detect them, or until now you cannot detect them. In the future, we hope it will be possible with 3rd generation GW telescopes, but the aim is opposite. It means we take the observed supermassive black holes and we want to reproduce them by making some history of seeds. So it's something that you want to reproduce. Is this the first objective?
Yes, I think, yeah. I think you basically modeled the history of a single quasar, as far as I understand.
Yes, yes.
So, okay, last question is actually from Boyuan and myself. I think it's very similar. How did you handle the spatial distribution of halos? It was not actually clear to me if you used Millennium simulation or just a semi-analytic model. And in any case, the small halos are unresolved. So how do you handle the spatial distribution and also the inhomogeneous metal enrichment?
So we don't resolve spatial resolution, but we adopt a presence sector in order to reproduce the number of halo and their mass in our comoving volume. But in order to reproduce inhomogeneous quantities, we have adopted, for the metallicity, a filling factor, where we are assuming that supernova bubbles, that we know how many supernova bubbles we have in each halo, are expanding. And we compute at each redshift the volume filling factor, and we define a probability of for a single halo to take from the AGM a certain amount of enriched medium. And for the Lyman-Werner radiation, we are adopting a non-bias. We also define a probability to find in the proximity of a certain halo as function of redshift, mass of the first halo, second halo, which is the probability to find a star-forming region in the nearby, according to the work of Dijkstra, Iliev, and so on. So we adopt probability.
Okay, but effectively, the halos are randomly distributed. The clustering is not modeled this. Is that correct?
In which, no, can you repeat?
Okay, maybe I'll do it on Slack later because I think.
Okay, thank you.
I will move to Slack. So thanks again, Federica.